他老师会保他，maybe，
你会帮我们
看情况，努力我就保。
？OK，这样子应该跟我说是他想让我 FYP 去做这个东西，来把它弄清楚，
可以啊，
因为我们现在还有很多东西没弄清楚。
肯定。
你料到这个了？
什么？
你已经料到这个了？
废话，我弄不清楚，你们怎么可能在半年就弄清楚？
什么？
我都弄不清楚，怎么可能3个月就弄清楚？
是不是？
对啊，但是至少要有人去开始去看东西。
所以你的意思是说，如果我们这个 STEM 进度很慢的话，FYP 继续做也是 unacceptable 的。
什么意思？
就如果我们这次 presentation 的东西不算很多，然后以后再继续去补的话，也是 acceptable。
当然是可以啊，这些题目分分钟都是一个 FYP 题目啊。
谢谢你啊，
对，
嗯，太欺负人了。
为什么欺负人？
你都读不懂的东西，指望我们做一个课 project 很懂。
我没有讲你要读懂它，但是你要去了解它。
这个读懂有什么差别？
啊，差别很大，太大了差别，
差别大到这个信息很快就被
没办法抄
那些靠我做
哦，其
当时我没有找，因为他那个你不懂讲解的时候，可以看你讲解，
那个超绝。
比较好听就参考。
而且没有，我是看一个小时，一个小时，就看特别多。因为那个
诶，怎么好像没有冷气这样？
什么？哦，你要看什么这里？那是人家放的，这两后是我放的。我干嘛不是你有个急了，这个你没新买吗？那他放了一个好奇给你看看留言。好奇，好奇，
我觉得是确实好奇，
要保持好奇。
诶，我傻逼，睡觉的都是做 FYP 咩？做到睡觉，他前一分钟还在问我东西。你睡什么觉？要讲好好的，不要怕，不要。
你可以，我希望你还好像有用。然后下一次，
最好不要，不要，因为 FYP 没有搞这种。哎，一言难尽啊，我也不是想搞啊，没有了。如果你不搞的话，学生怎么读？
不要把你保险的两边落成平时。
对啊，谁讲过？
You know who? You know who? You know.
啊，
万不能忘。
我要讲爱你。
但是那个他讲的那个人是你也知道那个人。啊，
你们讲，边国家的三个人形式也边国点的，边国我关键是国的旗号。
Lydia 他们呢？不知道。Okay, okay, let's recall what we did yesterday. So we have a brief idea on what storm check compactification is. Later, when more people come, maybe we'll discuss on some revision class and so on. Okay. And okay, so yesterday we compactify four things, right? Here. Okay, basically 1 to 3 is same thing, but we compactified it differently. Okay, so let's discuss one of the problem first. Where we embed this graph here, okay, into this topological sine curve. Let's draw this. Okay, wait. Yeah, so you get arbitrarily close to this line here. Okay, to compactify it, we need to add in this interval -1 to 1. Okay, and then we need to add in the starting point. So these point that we admit is 0 and 1. So this point is also 1. Okay, where this graph here is actually, let's call it hx equals to x and 7x. Okay, so we look at the closure, okay, closure of this thing here. Okay, closure of this for x in 0 to 1. Okay, and then we say that this compactification here, right, can help to extend this function here, right? How to extend this function? So basically, we define a function on 0 to 1. Okay, so we got a function here. I want to extend it to this compactification. How to extend it? You remember that this closure here is isomorphic to some y. Okay, y is equals to 0 to 1 union sum a. How to think of this a here? Okay, so your 0 to 1 is this um, open interval, right? How to think about a here? It is something in bijection with this limit point here. Okay, but how do you draw this limit point? Basically, this a is just some interval, okay, 0 to 1 plus a point. That's it. Okay. Only then after you apply this homeomorphism, it tells you how you put these lines together. Make sense? So basically, you got one line, two line, and one dot. So one dot, one line, and another line. So constitute this graph. This is the homeomorphism. Make sense? Okay, so this is what this homeomorphism doing. Basically, you put these line together in this way. Okay, and then we say that we could extend this map here, fx equal to sine 1 over x here, to be where write something here. So a bit weird, right? Thing like this, right? So this is actually this is this. Okay, so wait. Please wait for a moment. Right. Okay. So I think be precise, I need to write like this. Of sine x, okay, where x is in 0, then of x. Okay, and then my x is equals to x to be. Okay, so how to extend this map here? So we see that our h bar x here, okay, actually live inside R cross R, okay, and then how do we map it? So this map here is the okay. So y isomorphic to this, and then inject to this, and then we do a pi 2 mapping here. Okay, so meaning we send x sine 1 over x go to, sorry, x sine y here just go to y. Okay. So you imagine, you got this hs bar, right? You look like this. Okay. On x it look like this. So when it is at x, what do you get? You get sine and sine 1 over x. Then you output what? Sine 1 over x. Okay, so at the point of x, you output the same value as theta hs. But if you are not on the x sine x, on this point, then what do you output? For example, this point here. What point you output? So let me test that. So let's say this point we know what is it, right? This is this point should be 1 and sine 1, right? Okay. So 1 and sine 1 here, what does it output? Sine 1. Okay. Yeah, good. Okay, so sine 1 here. And then how about the rest here? The rest here, what do you get? Here is 0 cross something in between -1 and 1, right? So it's just the height. Okay, so again, you can plot out this curve, or you actually can plot this curve up. Okay, so you actually see this thing as a domain now. Okay, and then above this, so let me move this away, and then above this 1 sine 1 here, the height here should be sine 1. Okay, and then let's say at this point here, the height here should be 1. Good. So let me how should I put it up? So maybe I draw this 1 here. So here is sine 1. Okay, and then you follow the height of this curve. Okay, follow the domain of this curve. You from here grow up and then go down to -1, and then go up, go down, go up, like that. Okay, makes sense that. So far making sense? Making sense or not? Okay, so you go up and then go down and then go up, go down, go down, go up like that. Okay, but how about this line? Can you imagine how this line works in this graph? What happened to this line? What happened to this line? Sorry? What do you mean by rotation? How to rotate? What's the y value of this line? So basically, I ask you 0, 1. What's the height of 0, 1? 1, no? 0, 0.5, 0, 0.0, 0, 0, 0, negative 0.5, 0, negative 1. So what do you get? A linear line. Okay, so you got this line coming like that. Okay, on the it's not really planar, right? It's like going. I mean, here I'll say this. Okay, so this thing is not living on a planar, right? Can you imagine? Can you imagine? So do I have a line here? Not long enough. No. Maybe this one is long enough. Right. So if you look at the z-axis, right? Where's my z-axis? Hey, Raysha not here also. So the whole kampong is not here. Hey, Ivan, 你的组员没有在。Okay. Oh, so okay. So you see, this is your z-axis, right? Okay. And then what happened to your the y value of your pinpoint here. So you start somewhere. Okay, where's my plane? I need to get a plan first. So let's say this is a plan, and then this is a okay. I use this use this vector z-axis, and then you got the graph like a snake, right? Going like this into this portal here, and then the height also go like a snake, but this snake is like swirling around like that. Makes sense, Maybe take this away. Okay, so you basically start around here, right? And then you go down negative, and then you go up, right? And then you go down again. It's like the snake is waking up, Right? 还是招生帮我抓看，还是 Rachel， 还是招生找我一起？Yeah, maybe yeah, you come this side. Okay, all of you focus at the 1 sin 1 point. So 1 sin 1 start here, this side, right? Okay, start on the right side. Okay, and then you go down, right? You go down, go to the other side, and then you go up, right? So you go down, and then you go up, right? And then you go down, 1 to negative 1, and then you go from negative 1 to 1 again, right? OK， 看了，这个身子看得到吗？然后它在这样转，这样做，有吗？有看到吗？它在下面转嘛，现在给它拉上来转，会这样的，可以想到吗？因为它的 y value 从1到减1，然后它下面是这样的嘛，那你上面就要减1，可以想象吗？可以想象吗？从1 sin 1开始看 ，OK， 你从 sin 1开始移到1嘛 ，OK，then 从1开始移下来，它要移到减1了，对不对？把它下面的domain是这样折这样，可以明白吗 ？project 下来过后是这个折来的 project， 可以想象吗？现在我可以画出来，不太好画这种。来，各位，你找对手了。呀，它不是搬开是指啊，因为它会动啊，它的domain是会动的。你看这样子嘛，下去还会是这样嘛，它起来是这样嘛，对吧？1 sin 1，所以你应该要想成 1 sin 1 sin 1，这点是什么啊 ？And then the highest peak 那边是什么来的？应该 ，OK， 我不知道。Sin something, take if you want, yeah. Sin, okay, should be something less than 1 let's say 0.8, 0.811 like that， 明白吗？然后再下咯 ，OK。And then the green line 呢，它会放一个 linear line 在那里 ，linear line。看一下我画得出这个三维的东西。Thank you, Rachel. So something like this. OK， 所以你想象这个是那个 plane， 然后我们要不要移它一点点 ？Maybe 移它一点点。移它一点点。Okay, and then the linear line looks like this. Okay. And then the height is like this. Okay, and then horizontal line maybe like this. Make sense? 可以吗？可以想象吗？可以想象吗？这是这个的 graph 来的，这个的 graph。 Okay, so this xy plus this y here, 这个的 graph， 可以想象吗？ Can you imagine? So basically, all these points here, right, you attach with a height with their y value here.
Get the graph y and z it should be
Y and what do you mean?
value of y component and z is the same.
Y component, which y? Yeah, sure.
So I get that graph straight line.
No, right, because it also depend on your x, right? Because this is a R3 in R3, not R2. Yeah. If you like, I think it is true that this is true or not. Let me think. Maybe it's sitting on the y is equal to z plane. I think you are right that they are living on the y equal to z plane. So they are living on the same plane, is it? So this linear line and this graph here is living on the same plane. Y equal to z plane. You see, this is the y equal to z line. Yeah, I think you are a little bit right. So here is y equals to z plane, right? So here is y, here is z, here is x. Right. So actually, your thing is living on this plane. Make sense? Huh? Make sense? Yeah. Yeah. The thing is, yeah. Okay. So this is planar, right? It's planar. And then you add in the height. Okay. Yeah, you add the height in. 电脑写写. Yeah, so if you imagine the planar curve like this, right? But when you add the height, it becomes like this. Okay. Yeah, and then we claim that this map here is actually a continuous map. Okay, and that is an extension of this map here, sine 1 over x. Because when I restrict the evaluation onto this line here, it gives me sine 1 over x actually. Okay. Makes sense, huh? Okay. So this is how we extend a continuous function on the compactification of space. Okay. Got idea?
Cos y equal to z at all times.
Yeah.
And then the value of the sine is 0 to 1.
Yeah.
So I imagine the plane, but I slug the plane.
Yes.
And then the curve will go across.
Yes.
Maybe like around 1 to 4 of the quadrant.
Mm-hmm.
Assume for now. And then when I
Cool.
get the projection of y and z axis, I get like two axes in a straight line. So it moves like this, and then I squish and then get y z graph.
Oh yeah. So basically, this planar graph here shift to y equals z planar. I think that's the easier way to think about it. Yeah. Yes, that's right. You're right. Yeah, I think you are right actually. So this will become our general construction later. Okay, this will become our general construction. Okay. Yeah. Okay, so this is one way to compactify, right? But how about the other way, right? Actually, there are two more ways I taught you, right? So one of them is called the one-point compactification, where you just combine these two empty point here together, add in 1 point. Or I can just add in 2 points on the side, at the side. Okay. So also for this compactification, you also can think about this kind of way, right? So what the hash, let's say, what's the hash one we use here?
What is the hash1 we use here? What is the hash1 we use in this case? Okay, so maybe I bring it down. Okay, what's the hash1 we use here? This is just call, so hs bar of call sine 2 pi t, 2 pi x, and sine 2 pi x here. Okay.
And then you can also think of it as this kind of compactification. Okay, so where you compactify this set here, and then you put it as a y equal to z plane, because I use the same y.
Makes sense. Does it make sense? Okay. Wait, what did you have? Yeah, okay, good. So you understand send the link to my Teams, and then I can share it. Thank you. Okay, and then so the picture here is I embed this thing into R2 again. Okay, and then I can look at the graph of it. Get the graph of it. So let me draw this picture here. Okay, and then so it live in the. It doesn't matter. I think seems like you cannot see it, huh? So let me draw the plane again. Where's the y equal to z plane? It's like this. Okay, and then your circle live on this plane. Okay. Does it make sense or not? Makes sense, man. It's exactly what happens here. So you put your graph into R2 first, and then you slanted it. Okay. And then here is the same. You slanted it. Okay. And then we will say that, oh, this is the this projection plus all this homeomorphism stuff is the extension of this circle map. Is it an extension or not? Yes, right, because if you check on this point here, it still gives you sine 2 pi x. But this point here also have a coordinate already. Okay, what should be the coordinate of this point in this case? What do you think? What's the coordinate of this point? 0, what? 0, 1. Okay, sorry. 1, 0. Okay, so this y coordinate is 0. And how about the other case? How about the 1-point compactification case? Sorry, 2-point. So what we did here is we still put it into R only. Okay, we put it R only. Put it into R only. And then what do you do? Okay. Yeah, put it into R. And then what do we do? We put it into R. And then we try to complete this. Okay, we try to complete this. Oh, okay, so depends on what function you take on it. So for example, let's say this function is sending x to x is the identity function. Okay, is the identity function. Then we know what to add here, because this is just the 0 point and 1 point. Okay, and then what do we do next? Do we need to project anything or not? We don't really need to project, I think. This is just extending the function fx equal to x for x in 0 to 1, 2. So you extend it to fx bar. So let's say f bar x equals to x for x in 0 to 1. This is your extension. That's it. Okay. Or if you like, you can draw out the graph. Actually, what's this graph here? So this graph here actually is okay, I think I should draw this. The graph is like this. So 0 to 1. Okay, so this is the graph. So if you want to look at the graph, so let me go here. So if I want to draw this graph, so here, okay, 0 to 1. And then I draw this graph. So your curve become like this. Okay, this is your new extension of your graph. This is, to be precise, this is F bar. Okay. Yeah. So you can see, we extend our function to the compactification of the topological space. Okay. After we compactify, we can extend this function. Okay, what does it mean by extend the function? You extend, right? 变大嘛，变长嘛，意思说原来的东西还在。Okay, so you need to check on the original space, it gives you the same function you had before. Okay, at the new point, then you can make it continuous. Most importantly is this new guy here is continuous. Okay, otherwise I can simply extend one. I just send the limit point to anywhere. It's a function. But now the point here is I want to make it continuous. Okay, so let me make a remark here. This extension have to be continuous. Okay, not just a function, it should be continuous. Okay. Okay. Right. So, right. So before we mention about Cech compactification again, so let's prove a theorem. The topological space has a compactification. Why? Having the property that every bounded continuous map f from x to r extends uniquely to a continuous map y of y into R if and only if it is completely regular. Okay, so yesterday we defined a Cech compactification for completely regular space such that every bounded continuous map can be extended uniquely to a continuous map of what? Of y, okay, into R. So this y is a compactification. Well, yesterday we defined that a compactification is the compact Hausdorff space. Okay. So the compactification that have this property, we call it a Cech compactification. So it's like maximum. So if you think of the case just now, right? So I present you 1, 2, 3 way to compactify the open interval 0 to 1. This is just 3. Just now, this says that every bounded dot. Okay, every bounded, meaning what? Oh, I need to add in this line and this dot. I need to add in this dot. I need to add in these 2 dots. Depend on what continuous function. You need to add all those points into it to make your space compact, okay, under this continuous map here. Okay, how much thing we need to add in? So later, if got time, I will show you what is the Cech compactification of 0 to 1 open interval. I cannot show you the real thing. but I can show you how scary it is. Okay, yeah. 这个东西就很像鬼一样，你不知道那是什么，但是你就很怕它咯。有没有人讲得清楚鬼是什么啊？有吗？有没有人讲得清楚这个班上？啊，很想知道什么是鬼。然后啊，然后已经是开始有神学、玄学啊，玄学研究。Okay, so let's try. Okay, so yesterday we discussed that if you have a compactification, because you are subspace of okay, so what's the reason? So basically, because you are subspace of a completely regular space, because your compact space is your compactification Y is already compact whole stuff, so it's already normal, which is completely regular. So being a subspace of a completely regular space, you are completely regular. Okay, so X is already completely regular. Okay, do you know this it refer to who? This it is the X, not Y. Y is completely regular, is very normal because Y is already compact. Okay, but now it's about X. Then how about the other direction? We want to prove that if X is completely regular, then I can construct this Y. Okay, I can construct this Y here. Okay, so let's see how we construct it. Actually, this construction is what you have seen before. Okay, it's very similar to what we did just now. So suppose that X is completely regular. Okay, so there are basically two steps now you need to do. So first step is you need to find this compactification. Second step is you need to prove that every bounded map extends uniquely. Okay, this is the two things you need to do. Okay, so first is the existence. Okay, you find this Y and prove that it's compact Hausdorff and then got the compactification property. Second is you need to show that every bounded continuous map here can extend to a unique map. Okay, I think we will focus on doing the first step, and then second one we will leave it for you to read because it's really a general statement that on what we have did. Okay, let's see how we construct this Y here. So because you see 人家已经告诉你我要这样东西有这个 property 的，所以重点在哪里？我要确保这个 property work。I'll check about this property work. So since we care about every bounded continuous map, right? Why not just look at, so let's call this BCX. Just look at the collection of all continuous bounded real valued function. Okay, so we try to use this property that our client want, okay, to make up our space Y. Okay, 人家讲要这个你就做给他。And let's try and use this. So what we can do is from this function, right? So what's the property of this function have? So actually there exists a closed and bounded interval. Let's call it IF, depend on F because who knows where your image lies. Okay, that contains your image. Why can you do that? Because my function is bounded. Obviously the image is bounded. But if it's bounded, then obviously you can find a closed interval in R, correct or not? Okay, to contain your image. Then here is the magic thing we're going to consider here. So we'll consider the product of this guy. Okay, we consider the product of this guy. Every function, I go and find this IF here. Can ma, right? Because I'm bounded, my bounded function, because my image is bounded. So I found the interval that bound my image. Okay, and close. And moreover, what we observe here, obviously, this is living in the product space of all product space of R indexed by the function, correct or not? Because every interval live in one R. Okay, how big is this? So last time, how we describe about this? How do we describe about this space here? Infinite product space. Actually, you can think of it as a function from the index set to the space. Okay, or sometimes some useful word for those who would take function analysis here is this space actually is a dual space. Okay, dual space means what? Is a space of function defined on this BCX. Evaluate to the field. That field, this one field. So, but this one has to be a vector space, right? I mean, it's not hard to check. If you put two bounded things together, vector field just pass, right? You add them, it's still bounded, still continuous. You scale by the scalar, still bounded, still continuous. So it's a vector space. Okay. So function, you guys learned ALL before, right? Okay, dual space of a vector space. Okay, so functions, sending a function to its field, the ground field. Evaluate. Okay, so why is this description useful? So this, in this case here, we could construct this function called the evaluation function. H from X to this product space here. IF, sending X to Fx, such that F is in Cx. Okay, so this is the embedding we want to do here. Okay. Okay, familiar or not? This embedding here. The little H just now we send X to sine 1 over X. And then this one I just send it to more continuous function. Okay, a lot of them. Don't know how many. Okay, so now actually this is a lemma that I'm not gonna prove here, but you can check in the notes later. So you actually need to prove that this hash X here is an embedding. Okay, meaning you need to show it is injective of X into a, what kind of space is this? Closed and bounded in R. Closed and bounded in R means what? Compact. But you have infinitely many compacting product together. What do you get? You still get a compact, because Tikhonov theorem we proved last time. And moreover, it is a very nice Hausdorff space. Okay, so it's a compact Hausdorff space actually. Okay, so that's why we need to restrict to IF. That's the reason why we don't want to look at the whole R. The whole R is not compact. And by Tikhonov. So now, how do we construct our Y? So you just take the closure of hash X, like what we did just now. Okay, take the closure of hash X as a closed subset of a compact T2 space, compact Hausdorff, fancy a bit, right? T2 here. So the space here actually is the compactification U-bar. It's exactly what we did just now, just that you add all the bounded continuous function in. Okay. Okay, so it's not exactly HS bar, if you remember. It should be something homeomorphic to HS bar here. Makes sense? Because you should think about the example just now, because you might think that this line here is not living here actually. It's just that I try to embed this line into here. Okay, and then from this, I only can add in the limit. How do I add in the limit? Actually, it's based on the graph that I had just now. Okay, based on the graph I had just now. Based on this graph. Okay, because you can see here that there's plenty of way to make this compact. Okay, you can put 2 dots, become compact, or you can just put 1 dot, make it compact. Few ways to do it. So how to describe this different way is how you see this line here in different. And in different way, then we compactify in different. Okay, huh? Okay. Hey, by the way, yesterday we still talk about this example, right? This example, how we compactify this, 0, okay, not 0 to something, right? Is including 0 here. How we compactify this, we use this needle here plus a circle. Do you remember how it goes? How we do this? Remember we do this, right? Okay, and then we put the circle in. Okay, to compactify. Okay, so actually it's a point plus a line plus a circle. Okay, to make this line here compact. Okay, make sense? Does it make sense? Okay, right. Hey, this kind of thing, is it appearing in your dynamical system? Is it appearing in your dynamical system here? This swelling thing here. Okay. Maybe if you want to make your space compact, then you need to do some compactification to it. Maybe then your solution set will look nice, maybe. Yeah. Okay. Okay. Right. Then how about extension? How to extend then? How to extend? So how about how to extend? So existence of the extension how to do? So I will just write it to you what is going on here. So first of all, you have y here, which is isomorphic to your hx bar here, right? Again, this can be sit inside. Okay, so maybe I write it here. Y isomorphic to hx bar. Okay, that can sit inside this product space that we defined just now. Or not? Okay, and then what to do? You just do projection to IG. So here is a projection to IG if you want to extend G. 赵胜，可以对不对？ Because I already include all the possibility here. G is just one of the bounded continuous function. I can find the projection. Okay, because I already have all the possibilities. Okay, so if I want to extend G, I just compose this together, project to the IG component. 画图。Yeah, thank you. 幸好你没有睡到不见去。Okay, so it's like what we did just now. Okay, it's exactly like what we did just now, right? And we project to the component. The second component is the function that we define, right? That's the second component. And so we map to the component that define the G part and the G value. Okay, and then next thing is you prove uniqueness. Okay, uniqueness is quite interesting actually. You should go through it. I put into the notes already. Okay. Okay, makes sense. So actually, 这个是蛮抽象的，其实。Just now we got one function, then I can fill it in for you, right? So imagine you want to fill for every f, or how should we imagine it? I'm not too sure. Yeah. So you need to imagine that this y is already filled up for all f. So just now I already give you 3 possibility on filling the open interval 1, right? Okay, either you put 1 dot in. So 1 dot, at least the one of the dot need to be inside y already. And then there's a 2 dot
compactification. So now you got 3 dots. And then just now the other example, let's add one close interval, a line plus a dot. So you got 4 dots plus 1 line already. But this is just 3 examples only. This one need all 全部. Okay, so there's a lot of things you need to add into it. Later we'll briefly discuss what we will get. How big is this Cech compactification for 0 to 1 open interval? Okay. Okay. So a corollary here is topological space is completely regular if and only if it is a subspace of a compact T2 space. Okay, so why is it so? Just now we said that, if it is completely regular, it has a compactification. But what does that we say about compactification yesterday? X bar is equals to Y. Okay, X bar equals to Y means what? X is dense inside Y. Okay, so actually, if your space is a completely regular topological space, your space is actually dense inside a compact Hausdorff space. Sorry, yeah, compact Hausdorff space. Okay, so obviously you are a subspace there lah. Okay, make sense? Okay, you are dense set inside it. So let's write it down. So if you have Y, then this is called Y. So X bar equals to Y, where Y is yesterday we defined what is it already, right? Stone check here. Compactification. Compactification of X. Y is a relation of X, which is compact and T2. Okay. Okay, so if you want to ask, whether I can separate a closed set and a point inside a graph using inside a space using function or not, only if you could be a subspace of a compact T2 space. Only you can do that. Okay, so you see, compactness is quite important here in this case. Hausdorff, yeah. Okay. So this separation is a little bit different from the separation you know, right, on open set. Completely regular, actually you need to use function to separate. Okay, but compact and T2 is something about open set. Okay, so something about open set to tell you whether you can define a function or not. Okay, so this is the power of this corollary. Make sense? And if you can define a function, it also can tell you what's the topology there. Okay, so the second statement here is about open set only. But the first statement involves function. Where you need to be able to define a function. Okay. Yeah. Make sense? Okay, so this corollary actually quite strong. We can relate two different things. Quite different thing. Okay. Maybe. Let me see what else we can do. Okay, maybe we will stay without proving. Then later, after break, I tell you something about Cech compactification of 0, 1. Okay, so without proving, I want to show you something. First is let me see. This statement here. Hey, where's my statement? Let me check. Stone check.
My statement disappeared. Oh, so wow, interesting, huh? The order drop. Let me see that. I think I messed up something here. Yeah, so this one disappeared. This one should be belong to who one? Now, let's go this now. This one is 1, 2, 3. Okay, this one jump. Okay, this one should be here. Okay, so one statement is if you are completely regular space, just now we proved that it has a Stonechek compactification. So given any continuous map from X to Z, now it's to Z and not to R. Just now we are to R, right? Just now we are going to R. Now to Z, where Z is a compact hot space. Okay, R is not compact hot space, right? Then map. So the map F extend uniquely to a continuous map in G from this compactification. Stonechek compactification, we write Bx here to Z. So just now we map to R, but we restrict to bounded continuous. But now here no bounded continuous. But we replace the compact. We replace the codomain here to be a compact hotstop. So this is like a boundedness. No? Okay, boundedness we want. And then they say that this map will extend uniquely to a continuous map from the Stonechek configuration to Z. Okay. So you should think that this is a generalization of what the extension we can do for Stonechek to continuous function, bounded continuous map to real value, right? Okay. And then this is actually very fun proof because this proof is like considering the subspace inside this compare horizontal space of 0, 1 that we know last time. Okay, basically we put this Z back into this kind of space. Okay, and then we use some non-result we have proven. And then second, you can show that the Stonechek configuration is also unique out to homeomorphism. And this uniqueness proof is similar to what we proved yesterday about compactification is also unique out to. So this kind of property that we impose, right, is really, how to say, sometimes we call it a universal property. It's like, there's really one thing in this universe, one such thing, up to homeomorphism. Okay. Okay, any question before we take a break? Any question? Any question? Before we take a break? No. Okay, so let's break until 4:07. Yeah.
这笔记好像有问题啊。
OK，
你这个是 F2 还是 F3？ 哎，F2Q 应该是 F2Q 吧？
应该是。
对，这个好像是我们的三个题。对，然后刚我们在讨论了，
对，
然后我发现东西，我跟九号想的东西不一样。
什么意思？
就是他认为我应该做的东西跟我做的东西是不一样的。
哦，OK，所以
在有点头痛。
你做的东西有用吗？
有，可是没有很大用。
没有很大用。可是你的 abstract 不是 Seng 了没
生好啊，
不是在做那个东西？
是，应该说不完全是，应该算是有三种都有。因为之前他上面是来的时候，我没
我没有 reply 他，我没有看 message，然后我到今天才看 message 说，我刚才 reply 他，那他刚跟我讲，他才是他讲他，因为他直接写我的，然后送给你。
对对对，可是你 topic 呢
？topic
？topic 一样吗？
类似哦，
哦，类似啊。
我
OK
topic
这样他没有找到你，还讲哪里的照片呢？
我照片我送给他，他之前就有讲照片了，可是 abstract 跟 title 我没看到，所以我没有 send 到，没有 send 到给他。然后这个是什么？所以现在我要临时找那个 classification of financial group 3种都要，然后还要做这个 double cover，直接投放。这 presentation 是确定是1组2个小时的。
嗯，
诶，我在想一个人到底要讲多久？因为还有问题啊。
对，20分钟
20分钟，
像个 FYP 的时间，
我讲15分钟够了。
够15分钟就。
你反正就是很多东西，
最长我是说最长，我不是讲至少啊，我是说最长的10分钟。
啊，最少20分钟。
对啊，
昨天跟我说至少。
我有讲至少没？
有。
啊，我忘记了，忘记了，
完蛋了。
没有，不可能，因为你自己想一下，哪里有可能呢？因为我们还有 Q&A 嘛。
Q&A 你说就5分钟是
但是你自己想一下，你们5个人哦。
？OK，understand。所以你的意思是15分钟就够
，15分钟应该要
差不多是吗？
差不
15到20哦，每个人。
15到20公里吧。
差不多。
OK，
8点到6点。地点在你啊？
对啊，地点在哪里？
哎，我还没有 post 呢。
你没。
哦，我还没 post，因为我本来是等他们那个 poster 直接做出来，就是那个啊，
我可以把那个重新上传一遍吗？
什么意思？
那个 Word 我可以重新上传一遍，我之前终于把他的照片发了。
你直接问那个谁啊，那个啊，看他要不要收，他要收他就收，不收就没有了。
哦，他做那个 poster，
啊，是他做的。
那我 F 人带就可以改吗？
你看他愿不愿意帮你改哦，他愿意帮你改，你跟他讲说，你要快一点哦，你不要他们要 pause 了，等一下。你就现在发给他。
然后我就抄。
啊，你现在就做，你现在
回去。
你要快一点，不然的话，等下他们要share出来就来不及改。
Compactification of financial group 东西很多，不确定做完，可能会缩小范围，有可能拿完全部。
对，
因为我是剩1天时间，我要赶完它不？刚好没有上课，晚上才对吧？
我好奇，我们的 reporting。
对啊，这个就是为什么我放了一个星期的 gap 给你看。
OK。
给你们的。
如果我的 details 说你这个 top 拿，这样我的 reference 两些。
我也有 reference 嘛，对不对？我的东西。
你的 reference 就好啊。那我把你的 reference 三个写下去好啊。
你可以去证实一下吗？反正我一定是从那里面拿出来的，可以去证实一下。
我去找。没有人算。有 reference 在你啊。
在下面在第一秒的。
4个，5个。
写下去。我等我做好之后我去看。
哎，
可以换排名，可以换排名吗？
为什么
？present 的排名。
你们自己组内还是整组的？
整组跟别的组换的。
我们已经 fix 好了。
对啊，如果跟别的组换。
为什么呢？
讲第一个。
不能，因为第一、第二他们是有事情的。应该不能换了。怎么聊第一个？
因为我们讲到第一个，然后找结束。
啊，不能，你们一定要压轴。因为你们里面有问题。
好，
我要给你们压轴。然后我们要从连题和排名都不想压轴
啊，
然后你就叫我们压轴。
我就是要给你们压轴。你们会算哪个 example 出来啊？
我的版没 example，
是筛验算。
应该有，
应该是筛验，就是筛验做不了。
也是有一点。
应该也有。
它是
筛验会做哪一个算法
？Equation 的 example。
筛验会做哪个算法？
之前跟你讨论这个。
没有，他只是讨论那个算法，我不知道他要 present 哪一个例子。
没有做完出来。
你们没有讨论咩？
我们有讲要 send 那个 rough 出来，可是现在剩还应该没有上吧？然后我们在讨论这，我没有看那东西，因为我东西出问题了，我在做东西。
OK，
他们就没有来，他们现在还在做这，我没办法，我电脑没有电，我就只能过来。
OK， 他们是一起做啊。
我们全部在 B1 做的。
所以现在他们还坐在那边做
应该吧，
，OK，
我也不确定。
早就要坐在一起做了，
还可以吧。
不是早就要坐在一起做了
一。个礼拜的 meeting 也只是去外面，然后讨论完，然后分配了工作，然后啥都没有坐一起做啊。可是可能明天会啊，因为要做 PPT，现在有点头痛，因为我的因为我目前做东西还叫我做 Compactification of the financial group，然后我要做 double cover，
OK，
然后做完过后才做那个 equation。
OK，
可是他们
我的 reference 是准的，我肯定是从那几本看来的。
对，没有，可是这有个问题就是他们讲说，就是我如果讲 calculation 的东西，然后突然之间去讲 equation 会不会很奇怪，就是很不 relation。
那你们怎样去 present 它？我也不确定。
就要讲很不 relation 啊，然后
OK
我就想说，干脆想说，就是
Yeah
如果我先讲一半，然后看他们讲完了过后，到我要的话再讲。可是我接着下去就是语调的话，我的 equation 还要用到，所以我还是要 prove 出来。
是吧？可能你会讲，可能 maybe 你讲了一点，他再重复那一点，something like that。
我觉得还应该是一笔带过。你也
对啊，一
他没有
笔带过啊，所以你要讲啊，
他没有要
他要用
接着
罢了，他是要用你的东西。
嗯，
对啊，
因为
连你要讲
他们
完
4个都要用我的东西。
哦，OK，
没有办法，
不错。
有几个人来？
来么？
来6。
我没有叫哦，有一个会来啊，有一个从英国回来的会来。其他我就不知道谁会来了。啊，right， 所以竟然在这边 ，hello。So this Saturday, right, we have algebra geometry seminar from morning 8 o'clock to 6 o'clock. So we have lunch at 12 to 2. So if you want to come, you are welcome to come. So the place is 不要我请好不好？你自己去跟你算了，在 record 着。去跟你的嘟讲一下，好吧？真的要气死我了。在隔壁楼，隔壁楼。啊？谁讲谁来的？隔壁楼有谁？我问你。没有这样隔壁，那隔壁算了啊，现在是隔壁的隔壁。隔壁的隔壁。等一下我 check 一下那个classroom 在哪里哈？看可以。So the classroom is at A4G07. Okay, I remember. It's a lecture hall. Actually, we are making the poster. You could wait for the poster announcement. I think by today or tomorrow morning, they will post it up. They will advertise in IG and your Teams. Huh? Who take away? Take away the poster. So I think it's a student council. Yeah, student council. Thank you. Thank you for the so yeah. Good. Yeah. So welcome. You should come. And for the 2309 student. Who are the 2309 student here? Can I see where are you? 2309. 2309. 看得到吗？2309啊，是谁啊？金鱼2309. Okay, so I encourage you to come. Okay, at least come to some of them. So if you are interested to get my FYP, maybe you should come. Okay, listen to what. Actually, the topic is what I'm interested in. Okay, so you could come and listen. What's the flavor of research topic? Okay, yeah, presented by. I think we have second year, third year master student in that class. Yeah, and then I purposely break them off. So basically, every group will have second year, third year, and master student. So it's an even group. And so it's not like too advanced or too weak. Okay, right. So let's discuss about storm Cech compactification. So basically, I cannot find a proper discussion on this other than this block, topology block, Denmark. You can go and find Denmark here. Okay, Denmark's topology block. So he discussed about storm check compactification here. So it's not hard to see that if there are two spaces are homeomorphic, then their storm check compactification is homeomorphic as well. So since 0, 1 is homeomorphic to R, then we might as well look at the storm check compactification. Storm check compactification of R. So first question we want to ask, if I compactify R, right? I mean, use storm check compactification, is it S1 or not? We know that we add 1 point compactification is S1, but is that or not? Is it that? But I think from the example we see just now, right, it should be slightly larger. I mean, it should be larger than S1, okay, because we have 2 point compactification and so on. Okay, so one counter example we gave here is look at the CDF. I think you guys know better CDF than me, right? Well, where did you learn? Probability, you fail your probability, is it? CDF of the standard normal distribution. Okay, so basically you look at this graph here. So you know from CDF that this evaluation, right? At most you only get 1, right? And then you grow from 0. Like that, CDF. So this is a perfectly good continuous function, very continuous, Okay. But then, can we extend this function on S1 or not? Can or not? Yesterday, we talked about this, right? How should we extend? You want to extend to S1. Left and the right limit have to be the same. Okay? Let's tell Prof. Deal that you cannot extend this function to S1. Okay. Yeah. Okay. And then ask second question. 2 point compactification, is it storm check compactification? Okay, is it enough or not? Okay, just now 1 point not enough, right? 2 point enough or not? Okay, still no. Just now we showed the example, right? Topological sine curve. Okay, you cannot just fill in 0 and 1 and then continuous. No, because your limit point is more than 0. You need the whole line. Okay, the 0 is not enough. Okay, not enough. So then what should the storm check compactification of R be? Okay, what is it? What should it be? So if BR is this, right, we should be able to extend, let's say, this kind of function, x sine x. Okay, x sine x here. So how do we extend this? Wow, so this is getting technical now. Should we talk about this? Let me see. What's this technical thing? Yeah, should we? Is it? I think Seng's already taught until this stage. Let's talk about it. So let's read it first. Let me read together with you. So for every t in -1 to 1, so you should think of it as a point in the core domain. We let AT to be x in R. So this should be for the domain such that Wx equal to sine x equals to t. So what's W here? Yeah, W we define it as a sine x. So basically it's all the pre-image such that sine x equals to t. Okay, we fix a t and then we look at the pre-image. For example, the pre-image of 0 is the multiple of n pi here. Okay, make sense? Okay. So furthermore, you should check that. Let me see. Furthermore, for every t in the -1 to 1, let Bt be the inverse of t, which is a compact set in BR. Okay, so whatever let Bt is a compact set. Pi here is 1. Oh, okay. So let's say, do we assume it to be extend already? Oh, okay, yeah. So now we assume BR as this. Okay, we assume BR as this. We can storm check compactify it. And then we have this phi map that is already an extension. So now you look at the pre-image of sine x, okay, AT. Second, you look at BT. Two things, 两个东西，一个 AT， 一个 BT, AB. So what is BT here? Because just now we look at the pre-image of sine x, right? Now we look at the pre-image of phi under phi, pre-image under phi. But I want it to be compact set. Pre-image is compact. Okay, it is a compact set, right? Because this is a closed set.
closed in a compact set is compact. Okay, it's a closed set. This is a closed set, right? For those who take algebraic geometry here, Zariski closed this thing here. Okay, not Zariski closed because this is not a polynomial, but this should define a closed set. Why? Huh? So it's not Zariski closed, but it's another closed. You should see that it's another closed thing, right? Maybe you can show that its complement is open. Okay. So you see, so look at R sitting inside this Cech configuration. Okay, look at the embedding here. So for every T, right, you should see that AT is an inverse of, is a subset of BT because BT is something larger. Right, it's something larger. Okay, because this phi restrict to R is just sign. So it should contain all the sign inverse here. But what can you see here? AT is actually discrete in R. So actually, because sign is like this, right? So if you look at one T, so if you look at one of the T, it should be discrete. They're quite far from each other. Look at one T, it should be discrete. Okay, so one example is this pre-mesh of 0. But we know that each AT, but not in BT. Let me see. Each AT is discrete in R, but not in BT. BR being an infinite subset of a compact set. Infinite set of a compact set in R. Okay, good. So we know that AT is discrete in R, but it's not quite discrete in this compact set here, the Cech compactification, because it is an infinite subset of compact set. But last time we showed that compactness implies limit point compact. Okay, so limit point compact says that every subset should what? I forgot already. I also forget the definition. So can you look it up? What is the limit point compactification? Every infinite subset has a limit point. It could contain all its limit point. What's the definition? Yeah, Dawson is looking for it. What? Has a limit point, right? Okay, so you have a limit point. So this means that the complement of AT in BT is non-empty. Okay. So there's something extra there. So here we see that we at least added uncountably many points. Okay, that's in bijection with -1 to 1. Okay, at least added in this many, right? Because for every AT, right? For every set of AT, we add limit point. Okay, for every T in the -1 to 1, we add limit point to AT. Okay, at least added uncountably many. But also we note that BM intercept BN is empty. Okay, being the inverse image of different point. So in fact, how big is the Cech configuration of 0, 1 or real number here? Actually, is the power set of R. 好像我们在班上面有讲过这个东西吗 ？Power set of R 没有，我们只有讲过 power set of N，which is R， which is SPS R。把这个是比 continue 那个 continue 还大一级。
不一定是
啊？不一定是一级。Okay, it's not assuming hypothesis. Okay, yeah, at least larger than R. Yeah, at least larger than R. Pretty big, is the infinity that we never met before. 我们没有看过这么大的东西，知道 ？Yes. Oh, I think yeah, you're right. Yeah, we should write it like this. Good, thank you. So this proof you can find in this book here. So in this book here, they also prove that the Cech configuration of R is equal to the Cech configuration of rational number and Cech configuration of natural number. Okay, it didn't say that they are isomorphic. It just said that it is same size. Yeah, same size. How it looks like, I don't know.
Okay, but not that let me see. So not that the cardinality of every first countable compared Hausdorff space is at most uncountable. So it's by another book. So we see that why I bring out this point here is we continue to look at what's the topology of VR here, like the Seng configuration. So meaning that it cannot be first countable. First countable says what? Every point will have a countable basis. So 给不了更大那个 base 那个 topology。OK， 每一个点哦 ，OK， 每一个点 ，right，every point， 这个是可能有一个点 ，OK，maybe there is some point that don't have countable basis， 所以可能你要很多东西来包住。OK， these points at which is not countable actually 就来在这边，属于是不是那个 not first countable 的 point，actually 就是你多加进去的那些点。Because 我 prove 过 R 是 first countable 对吗？ I mean every metric space is first countable, right? Yeah, so in particular R is first countable. So what's the first countable? You just take the ball with radius 1 over n. N is countable. Okay, but exactly those 你要 prove 啦 those points that not first countable is this. Because 那你知道有些是 first countable 的 so actually you need to prove. So if it is not first countable, meaning what? BR is the space that you cannot metrizable. Not metric space. 可以讲 not metric space 不太对 meaning the topology that we put on BR cannot come from matrix. Okay. Make sense? Okay, so this is a giant. 这个 giant so yesterday maybe let's see on which day is that Monday we have a talk on model theory. So this they provide a strong check compactification of n to the power k double, right? Just now we just discussed about compactification of n, right? RQ, right? Already as large as 2 to the c, but this one they look at the storm check compactification of k double. Quite ridiculous, I think. Not to my knowledge. Yeah. So first, what they do is they look at the extension of n, call it n star. So extension of n meaning you should contain n not infinite number. Again, and then the whole thing should behave like n, and then they put in those what do we call it? The sentence. Okay, the sentence that word is n also word in this n side. Basically, what they mentioned yesterday was this n star is a bit like a power set of n. Power set of n. Morally, it's a power set of n. And then after they define equivalent class here, and then taking the quotient, you will become a strong check compactification. Use the same notation. Okay, your notation done in this class is quite standardized. And so that you go to a seminar, you can understand what's the object that you play with. Okay. Yeah, any questions so far? Any questions so far? Any questions so far? Any questions so far? We're really close to the end of this course already. So we are finishing all the compact stuff. The last bit of the lecture, I want to do a bit finishing on the complete metric space.
which I will mention on Ascoli's theorem. Have you heard about Ascoli theorem? No, no, huh? Okay. Yeah. So what should I do? Should I do Ascoli theorem or should I discuss your assignment? Huh? Huh? We can let the assignment to later also if you like. I mean, I need to discuss at some point. Either I do it in class or either I do it in revision. Up to you. Yeah, revision haven't fixed yet. So do you have exam on revision week? Got no got some. I think some of the graduate course got exam during the revision week. I think so. So your revision week is free, huh? Okay. How about do it on Friday? Friday How about Friday? Yeah. 有考试几点? Yeah, I think someone have an exam because those courses with graduation student got exam. 9到11哈，我们要不要做下午？下午 maybe 2 to 3 or 2 to 4, 2 to 4, 2 to 4, yeah. And then I want to also to organize a FYP recruitment for 2309 batch. Yeah. So yeah, FYP recruitment. So but for the other batch already either graduate, either have the supervisor already, right? So is there a chance? Yeah, that's what I thought. Maybe we'll do it after the class, 4 to 5. Yeah, so the point of this recruitment drive.
Yeah, FYP recruitment drive. Okay, so for this FYP recruitment drive, right? I invite all the 2409. So sorry, 2309. Again, where is the 2309? Jingyu, right? Xiaoye, okay, and then Ian, all of you can come, Jia Yi, and also Hong Rui. Even if you don't want to do, like, you haven't decided, if you don't want to do FYP with me, you don't need to come. But you haven't decided, you can come and listen and then see what's the choice, or you give me feedback what you like, then I can put it onto the list, and then if you like, you can pick it on. Yeah, other than that, or I don't have, I mean, if I have too many students, maybe I cannot pick you or something like that. So if you like, you can pick me. If not, you can have a few choices. Yeah. Not sure yet, not sure. Yeah, some also depend on do I get any master student. Okay, but you are welcome to come. Okay, so tentatively for now, I think let's fix revision class from 2 to 4, and then 4 to 5 is FYP recruitment driver. And then hopefully I can invite the previous FYP to come and share what they do. Maybe you can continue what they did, right? You can continue what they do. And they already write out a pretty good account on what they have learned or what they studied. Hopefully this can help you to continue. Okay, make sense or not? Okay, so 没有哦，你没有回来啊？哎呦，你没有回来啊？再看啊，再看怎样？OK， 再看怎样？Yeah. Okay. So I'll mention this again. 哦，对，这边还有一个还有一个 row 型在这里忘记掉，全部在这里去，忘记了这里还有一个 row 型。Okay, yeah. So if you don't want to do FYP with me, you don't need to come. But if you are unsure, you want to hear any interesting stuff, you can come and join. Give some feedback. Okay, so revision class, we have to do physical. And some of you must come. So we must have physical first before we can do online. This is the school rules, not my rule.
maybe if you want to abuse the rule. Huh? No lah, I mean if you can come, you have to come physical. Okay. Yeah. Huh? 什么? Yeah. And then I think we will do the AG version in morning also lah. Next. Revision. You also got exam. Oh, 你们什么 class? A2 啊。
那就估计他生死了。
我可能去1:30，你要来因为考生的 replacement 也是3:30。
Replacement 在 revision week？ 什么 replacement？ No, sorry. We are revision week, not next week. Sorry. Not next week. It's a revision week. Not next week. Next week too early. I haven't done my marking later. Revision. Thursday. I was thinking one day. See how. 11，你说11到1点啊？这样我吃饭就1到2点，是吗？你考到11点吗？对不对？如果再迟，不是变5到6？啊，如果我发10到12，可能你来1个钟这样 ，maybe。Yeah, discuss it later 啦 ，AG discuss 啦。Yeah, now no point to discuss 了。你说你要弄，我不是为了你弄。我本来是不想弄啊，因为应该那个班是大家就应该自己要知道自己做。我们再讨论啦，再讨论呀，在那个班再讨论，这个班也没有意义讨论，没有其他人在。Okay, so for now, let's fix the topology first. Okay, 4:30. Are you ready for new concept or not? If you're ready, you are fresh, then we can go on with the new stuff. Still fresh? I think quite fresh. 看到正月很醒了。Let's do new stuff first. Okay, maybe later we do assignment at one go. By the way, if you have any question about your marking, you can find me first. Because we already did that. Yeah, exactly. Yeah. I mean, if you have problem on my feedback, you can share with me. Okay. So what's the Ascoli theorem here? So the motivation is like this. So A in Rn is compact. Okay, if and only if what? It is C and B, BC, A, BC, closed and bounded. Then the next level we want to ask is, how about the set of continuous function? How about the set of continuous function defined from compact set to Rn? Okay, so first of all, you should ask yourself, why even this is a topological space, right? Okay. So whether we can ask, when is this thing compact? Can this be a compact thing or not? Okay, what's topology I put on this function space? What? Let me see. Did I define any topology here? What? Script C. What is script C? The set of continuous function. So this is a set that contains continuous function. Continuous function from a compact set to Rn, or general set to Rn. Okay. So later we'll define a topology on this C something to something. I will define it. I think how many topology I'm going to define here? For this purpose, we'll use something called uniform topology. Okay, so basically, maybe I can tell you first. So basically, actually, this set here is a metric space. Okay, we make it a metric space first. Meaning I want to measure the distance between two functions. Have you measured distance between two functions before? Difference of what? Function is defined at every point, right? So you want to compare every point. Maybe you can take the supremum. This is one way. Okay, there's some obvious way. 最远的距离. Okay, maybe some point is very close, but this doesn't represent this difference, right? Because some point could be larger. Then how about we just take the supremum of it? Okay. Obviously, you want this supremum to exist, right? Because supremum could go to infinity sometimes, right? So you want to make sure that supremum is finite. No, I didn't bound it. It's just continuous. But the point here is I put S as a compact set. It would achieve the maximum and minimum. So it becomes bounded. Okay, so then this supremum will make sense. Okay, this supremum will make sense here. And then from this sup metric here, induce a topology. You look at the open ball. So the ball here is a round function already. Where is the round function? The whole, you can imagine at the graph there. Yeah. Weierstrass theorem. What's the statement? Uniform that's in continuous function. Maybe it could be. It could be. It could be. Could be this, or should it be more precise one and more finer distance? I'm not sure. I'm not too sure. Okay. Anyway. So yeah. So how about this? When can we deduce compactness on this kind of set? Okay. Because yeah. Okay, so let's go on. Okay, so now the abstract stuff here is we already walked away from topological space being compact, something on topological space to a function space that defined on this topological space. Okay, it's a function space. Right. So let's define something to work with. So let Y be a metric space. And then let F be a subset of the set C from X to Y of continuous function from X to Y. Okay. So if X not in X, the set of function, we will define it to be equicontinuous. Okay. So you have seen continuous, right? You have seen uniform continuous, right? Okay. So we're going to define equicontinuous here. So where do we define this equicontinuous on? It's actually we define it on the set of function. Okay, it's not on function itself. Uniform continuous function. Uniform, oh sorry, continuous function, uniform continuous function, Lipschitz continuous function. But here is equicontinuous set of function. Okay, it's not on function, it's on the set of function. So look carefully. So we define it to be equicontinuous, and that's not if, yes. Sorry. Actually don't care. Care, do we care? Let me see. I think we care. Yeah, because we care. Okay, let's make it a metric space. Right. So let me get a metric space. But why the metric space I put here is like a real metric space? Is it just R? Oh, no, because in the next page it's a different D. Okay, so let's write like this. So X is with D and then Y is with D prime. Okay, if for all epsilon greater than 0, so this is the same setup, there is a delta greater than 0, such that for every X in X, and then this is a special part, for every F in big F here, right? For every function, they have to work for every function, such that if D of x naught here is less than delta, this implies that d prime of fx naught is less than epsilon. So you could think that need to true for all f, right? So this is how this name come from, equicontinuous. It's like 差不多一样的 continuous， 对吧？每个人都差不多一样，我都可以 make sure 到这样子，每一个 f。So we will say that it's equicontinuous. But this one is fixed for a point. So yeah, fixed for. Okay. So so if f is equicontinuous at every x naught, then it is equicontinuous. It's like how you define continuous also. Then next level, we define continuity, we can define uniform continuity, right? Similarly, here we can define uniform equicontinuous. So what do you think? How do I adjust this variable here? And what's the difference between continuity and uniform continuity? For x1, x2 in x, so we are not. So this line here, actually, there's a hidden property is here. For every s naught put in front first. Correct or not? Because I already fixed s naught already. So this s naught is at the front. But I can push this s naught back here. They become uniform. Very uniform equicontinuous. So this epsilon and delta, right, to work from random x naught. Random one. Okay, so then it will become uniform. So the word uniform is referred to the x direction. And the uniformness then refer to the x direction. Okay, so similarly, we can define that f is uniformly equicontinuous. Okay, so meaning we don't care about which point we fix on. For every epsilon greater than 0, there exists a delta greater than 0 such that for every x and x naught in x, and for every f in script f, d of x prime less than delta imply d prime of fx prime less than epsilon. Okay, so your ruler can move. Okay, can move based on this epsilon and delta. But just now your ruler, right, need to fix at x naught first. But then only you move your epsilon, move your delta. But here I give you every epsilon, you go and move around your f. Okay, then doesn't care where the x and x. Okay, so what's the consequence you could have after define this? So the member of equicontinuous family of function are clearly continuous. Okay, so if you have this true for all f, right, it should be continuous because this is a continuity statement, right? Apart from this guy, is a continuous statement. Similarly, if you see, if you remove this f condition, right, this is just uniform continuity statement. So the equi part is really for all f in script f. Okay. Okay. So in this two case here, what did you notice? The first delta here would depend on epsilon and s naught, but the delta in the f here only depend on epsilon. Okay, so this is similar to continuity and uniform continuity. Okay, so let's look at some examples. See whether this example, this kind of set exists or not. So first, let's look at this leap m from s to y. So what's leap m from s to y? What do you think? This is the set of this Cech function. Okay, from the Cech function from x to y, but not that I have an m here. What do you think? What should this m be? This Cech function, what's the characterization of this Cech function? What's the thing you want? Yes. Okay, so actually we fix the Cech constant here to be at most m, not at exactly m. Exactly m is quite restrictive. So up to all the way up to m. Okay, we include it in here. Then we claim that this Lifshitz function is, this family here, lig m from x to y, is actually uniformly equicontinuous. Okay. So what do you need to check here? Did you know that Lifshitz function is it uniform continuous or not? Yes, right. Okay, so Lifshitz implies uniform continuous. Very strong, huh? So what do you pick for your delta actually? You just pick it to be delta over m here. Okay. Because all of these are less than m, so yeah, delta over m, epsilon over n will be enough. More generally, right? More generally, families of Holder continuous function. Again, you can refer to our tutorial question. We have a Holder continuous function. Have you seen Holder continuous function before? Not in class. There's some fixed constant alpha and fixed constant of m. Do you know how these constant put together? Do you still remember what's the form it takes? Eric? Do you still remember what's the form it takes? What's the form? So okay, before that, so Lifshitz says what? Lifshitz says that fx minus fy is less than or equals to m of d of xy, right? Okay, so how about Holder here? Like this, m to the a. A appear at here. Okay, A appear here. So makes sense. Okay, good. So I like your logical thinking. So for Lifshitz, right, A is 1, but here is to some power. Okay, A here. Okay. So, and then we claim that this family is also uniformly equicontinuous. Uniformly equicontinuous. Okay, but what's the epsilon you take? So you can consider, you could consider taking delta equals to epsilon over m to the 1 over alpha. Okay, to get to check. Actually, I wrote it down here. So actually, I wrote it down because I know that I will forget. Okay, so this is it. Okay, it's alpha equal to 1 is Lifshitz. Okay. Okay, maybe one more before we finish. So second, look at this family. Okay, so this family of function. So basically, this is fn x equals x to n. I think this one we discussed in class. This Sn here. I think this one we discussed in class, in MA1 class. If you remember the picture, like this, and then like this. Correct. And then you go all the way like this, maybe. Yeah. Okay. Then this set, this set of this set of family is actually not equicontinuous. At which point? Can you guess at which point? At 1 actually. Okay. So to see this, I think I write down the reason. So to see this, not that. If x is less than 1, okay, then I compare this with my 1 here. So what do I get? Actually, I get 1 minus x to the n. And then you can make this as big, bigger than 1 over n as you like. Just pick your. Okay, so you cannot really control the epsilon and the delta properly. Okay. Okay, so before we finish, maybe we mention about one theorem before we finish. No need to prove, but so this is the theorem we're gonna say. So previously, right, we have a continuity of compact set imply uniform continuity. So same here, if you start with an equicontinuous family of function, okay, where X is a compact metric space, are pretty important here. We want to start with a compact set here because we want to make sure our image is bounded, right? Then F is actually uniformly equicontinuous. Okay, so previously we have compactness on the domain as well. Here we also have compactness on the domain as well. And then we can talk about equicontinuous family being uniformly equicontinuous. This is very similar proof to how you go from continuity to uniform. Very similar. Yeah, it's very similar. It's pretty similar. But it's very easy now because the compactness we use here is open cover, I think. Yeah, we'll be using open board. Yeah. Yeah, actually it's not too hard to prove. Okay. Yeah, what time is it? 4:49. Okay, then next we will go on define the submetric like I mentioned to you just now. Okay. And then we will have a uniform topology. Yeah, okay. No battery already. Okay, see you next week or Saturday if you come. 要不要再讲？不讲够了啊？Saturday